Hi class. Here's an example that might seem familiar. Say there are 10,000 puppies in a town. 8,000 are in homes, and 2,000 are in shelters. Every year, 30% of puppies in homes are dropped off in shelters, and 20% of the sheltered puppies get adopted. The question that you can ask is this. Question: what happens in the long run? This is fundamentally a question, surprisingly, about eigenvalues and eigenvectors. It is a question about Markov processes. That's what we're going to talk about today. Definition. A stochastic process is any sequence of outcomes where the outcomes at any stage depend on chance. A Markov process is a special kind of stochastic process. A Markov process is a stochastic process where 1, the set of outcomes, set of possible outcomes is finite. 2, the probability of the next outcome only depends on the outcome before. And 3, the probabilities are constant over time. This might seem like a lot, so let's just talk through our example that we've been working with. First thing that we need a start vector. This is our original state, and we know what this is. We have 8,000 puppies in homes and 2,000 puppies in shelters for an overall total of 10,000 puppies. We know what happens year over year. If this is the start vector, what happens next? Well, 70% of my homed puppies stay homed, and 20% of my sheltered puppies gain homes. This means that 30% of my homed puppies are dropped off at the shelter, and of course, 80% of my puppies in shelters remain in shelters. Let's actually look at this in terms of matrix multiplication. This is simply multiplication by the matrix 0.7, 0.2, 0.3, 0.8. This we're going to call matrix A, and this is going to be x1, which if we were to actually add this up is 6,000, 4,000. After 1 year, there are 6,000 puppies in homes and 4,000 puppies in shelters. We can, of course, keep going. After 2 years, x2 is just going to be a times x1. If you were to work it out, it's 5,000, 5,000. After 2 years, there are 5,000 puppies in homes and 5,000 in shelters. After 3 years, we're going to have x3, which is a times x2. If you were to work it out, this is 4,500 and 5,500. Okay, and of course, we can keep going. Let's put some labels on these. We have things called state vectors. These are the states, x1, x2, x3, etc. All the xi. These are individually state vectors. A Markov chain is a sequence of consecutive state vectors. For example, x3, x4, x5, etc. How do you get from one to the other? You get from x3 to x4 by multiplying by a, and from x4 to x5 by multiplying by a. This deserves a name. A is our transition matrix. All right. Last but not least, some descriptors. Definition. A matrix is stochastic if its columns are probability vectors. What does that mean? i.e., the entries are non-negative and the columns add up to 1. For example, our transition matrix, 0.7, 0.2, 0.3, and 0.8, its columns add to 1, so this is a stochastic matrix. Okay, now we have the setup. Let's do an example. The thing about Markov processes is that the long-term behavior of a Markov process is determined by the eigenvalues and eigenvectors of the transition matrix. This means that if you can model a process with a Markov process, figuring out what happens in the long term is as easy as just doing some linear algebra. The kinds of things that are modeled by Markov processes are things like weather and things like the spread of infectious diseases. We're going to do an example, but let's keep things light. The puppies example we already did in another video, so let's do another example. Say there's an island with 300,000 inhabitants. They can live in 3 places: on the beach, in the forest, or on the mountain. There's something interesting about the habits, the moving habits of the inhabitants of this island. Every year, 20% of the beach dwellers move to the forest, and 10% of the beach dwellers move to the mountains. We're going to represent this as B, F, and M, just to keep things short from now on. Every year, 20% of the forest dwellers move to the beach, 10% of the forest dwellers move to the mountains, 10% of the mountain dwellers move to the beach, and 10% of the mountain dwellers move to the forest. All right. In the beginning, 300,000 inhabitants, 150,000 live on the beach, 90,000 live in the forest, and 60,000 live on the mountain. And the question that we have to ask is, what happens in the long run? Okay. Step 1. Determine the start vector and the transition matrix. All right, so we just have to decide on an order. There's 150,000, 90,000, and 60,000. This is going to be our start vector. And we'll just agree from now on that the top represents the beach, the middle, the forest, and the third row, the mountains. We know, given the moving habits, that year over year, how many people end up on the beach? Well, it's going to be 70% of the people on the beach stay on the beach, 20% of those in the forest move to the beach, and 10% of those in the mountain move to the beach. 20% of those in the beach move to the forest, 70% of those in the forest stay in the forest, 10% of those in the mountain move to the forest, 10% of those in the beach move to the mountain, 10% of those in the forest move to the mountain, and 80% of those on the mountain stay living in the mountain. This is our transition matrix A. All right, step 2. Calculate the eigenvalues and eigenvectors of the transition matrix. Okay, remember that the eigenvalues are the roots of the equation, the determinant of A minus lambda I is equal to 0. You have a lot of practice doing this, so I'm just going to tell you what the eigenvalues are. They're going to be 1, 0.7, and 0.5. Now let's do the eigenvectors. For the first eigenvalue, 1, we're going to have to look at vectors in the null space of A minus 1i. This is this matrix, where -1 is applied down the diagonal. Okay, what's that? And we'll notice that this times the matrix 1, 1, 1 is the 0 vector. This here, 1, 1, 1, is the eigenvector corresponding to 1. Let's do the second one. 0.5. All right, we are going to again find the matrix A minus 0.5i. So we get 0.2, 0.2, 0.1. This matrix being A minus 0.5i. We'll notice that this times 1, -1, 0 is equal to the 0 vector. So this is the eigenvector. All right, last one. For the third eigenvalue, 0.7, we get this matrix. This being the matrix A minus 0.7 times I. You'll notice that this matrix times 1, 1, -2 is the 0 vector. So here we've got our eigenvector. Okay, we've got our eigenvalues, we've got our eigenvectors, and we'll note that there are 3 distinct eigenvalues. This means that we've got 3 linearly independent eigenvectors, and this means that A is diagonalizable. How do we diagonalize it? We set up X to be the matrix that has the eigenvectors in each column. We've got 1, 1, 1, 1, -1, 0, 1, 1, -2. This being the matrix X that we're looking for. We also need the diagonal matrix, D, which is going to be the eigenvalues down the diagonal and zeros elsewhere. This is going to be D. And then we also need to find X inverse. If we were just to find the inverse, I know you're pros at this by now, this is what we're going to have. This is X inverse. And these are all the ingredients that we need to diagonalize A. X inverse AX is going to be equal to D. Or we can rearrange this, of course. It says A is equal to XD X inverse. A to the n times the start vector is X to the n, which is the state vector after n years. We want to know what happens in the long run, so we're going to have to find the limit as n approaches infinity of a to the n times the initial state vector. And this is the limit as n approaches infinity of a to the n, which as a diagonalizable matrix can be expressed in a certain way. It's going to be x times d to the n times x inverse times our initial vector. All right, now let's just work this out. This limit as n approaches infinity affects this matrix. And what we get is x times this matrix, since a half to the n as n goes to infinity is 0, and 0.7 to the n as n goes to infinity is also 0, times x inverse times the initial vector. And what do we get? We get 100,000, 100,000, 100,000. This means that there's going to be 100,000 people on the beach, 100,000 people in the forest, and 100,000 people on the mountain. In the long run, there are equal number of inhabitants in each location. We've just finished our example of this particular Markov process, finding out what happens in the long run. With linear algebra, you can actually predict the future.